In this video, you will learn about means to measure the quality of the insulation of power transformers and bushings, such as power factor or dissipation factor measurement, and measuring capacitance. Possible causes for a reduction in insulation quality are also explained. The quality of the insulation in a power transformer can be directly measured. This measurement of the heating losses is commonly called dissipation factor or power factor. The smaller the dissipation factor or the power factor, the lower are the losses in the insulation, and so less energy is turned into heat. The level of dissipation can increase due to a number of factors: through aging of the insulation, due to the ingress of water into the insulation, or as a result of partial discharges. Measurement of the power factor or the dissipation factor is an important diagnostic tool to assess the quality of the insulation. At a particular frequency, for example 50 or 60 Hz, the behavior of the insulation can be represented with an equivalent circuit consisting of an ideal capacitor with a resistor in parallel. An ideal capacitor has no losses and a phase angle between the voltage and current of 90 degrees. As a result of the losses in a real system, represented by the resistor in the equivalent circuit, the phase angle differs from 90 degrees by the angle delta. The dissipation factor is defined as the tangent of this angle delta, hence its alternative name, tangent delta. Expressed in a different way, the dissipation factor is the ratio of the current flowing through the resistor and the current flowing through the ideal capacitor. The power factor cosine phi is defined as the ratio of the current flowing through the resistor in the equivalent circuit to the overall current. Conductive losses, which result in DC leakage currents, can best be represented with a parallel equivalent circuit. Polarization losses, which may result from AC voltages, can be represented by an equivalent circuit consisting of an ideal capacitor with a resistor in series. In principle, the power factor or the dissipation factor at power system frequency can be represented with a parallel or a series equivalent circuit. To get a better understanding of both types of losses, it is advantageous to measure the dissipation factor or the power factor over a broad frequency range. The angle delta can be very small for good insulation. A typical dissipation factor is 10 to the power of -5. This is like looking at a wristwatch from a distance of 2.5 kilometers. The mathematical correlation between the power factor and the dissipation factor is thus expressed. Since typical values are very small, the difference between the dissipation factor tangent delta and the power factor cosine phi can be neglected, which is why we will alternately refer to power factor or dissipation factor in this video and use only one diagram to show both factors. If the power factor or the dissipation factor is viewed over a wide frequency range, the parallel and series equivalent circuits show very different behavior. In the series circuit, it rises linearly with the frequency, whereas in the parallel circuit, it decreases hyperbolically with the frequency. The yellow curve shows the superposition of both effects. Transformer insulation consists of oil, spacers, and barriers. In the equivalent circuit, these elements are represented in black, red, and blue respectively. The equivalent circuit for real insulation is rather complex. The dissipation factor or the power factor depends strongly on the water content of the cellulose in oil. This curve is the result of relatively dry cellulose with water content of 0.2%. This curve has 4% water content. The Omicron TD1 can output voltages and currents in the frequency range of 15 to 400 Hz. The total losses in the dielectric comprise those resulting from the transport of electrons and ions and those caused by polarization effects. The losses depend on aging, water content, the proportion of conductive particles in the insulation, and partial discharges. The largest share of losses is known as interfacial polarization. Surfaces such as the interface between transformer oil and solid insulation, grain boundaries, or interphase boundaries may be charged with this effect. For bushings, the increasing dissipation factor indicates aging and decomposition of the insulation or the ingress of water. In some cases, badly connected electrodes or conductive control layers can be detected. Particularly on low-voltage bushings, cracks in the insulation and possible partial discharges can also be identified. For transformers, the power factor or the dissipation factor shows aging, water content of the oil and paper, and contamination with conductive particles. Besides the dissipation factor or the power factor, capacitance values are also required for the correct diagnosis of other problems. Capacitance values of bushings show whether there have been partial breakdowns between control layers. For resin-bonded paper bushings, cracks into which oil has leaked can also change the value of the capacitance. A rise in capacitance of more than 10% is normally considered to be dangerous, since it indicates that the insulation distance is no longer sufficient. For transformer windings, changes in the capacitance between the windings indicate a change in the leakage gap. This gap can change due to the deformations caused by high short-circuit currents and their corresponding forces.